Today, we're diving into a powerful, almost invisible chemical reaction that, and this is no exaggeration, literally runs our world. From the energy that powers your body to the tech in your hands, it is all driven by a simple, fundamental partnership.
So, let me ask you this. What could a rusty old car possibly have in common with the act of breathing? One is slow decay, the other keeps you alive. Well, it might seem like a riddle, but the answer is the exact same chemical reaction, just happening at wildly different speeds. And trust me, by the end of this, you are going to see it absolutely everywhere.
The key to that riddle lies in this chemical partnership, a constant give and take of energy and matter that powers just about everything.
It's called a redox reaction. Now I know, that sounds super technical, but the idea at its core is actually really simple. One substance loses these tiny little particles called electrons. That's called oxidation. And at the exact same moment, another substance gains those very same electrons, and that's reduction. The most important thing to remember is they are totally inseparable. You can't have one without the other.
The easiest way to think about it is like a simple transfer. Oxidation is the give. It's the one giving away electrons. And reduction is the take. It's the one accepting those electrons. Now, the name oxidation first came from reactions with, well, oxygen. But the real story, the definition that unlocks this huge universe of chemistry, is all about the electrons.
You know, the way we understand this whole process has actually evolved over time, and that's given us two main ways to think about it, starting with the original idea.
So the old school definition was all about oxygen. Take this reaction, for example. You've got copper oxide and carbon. The carbon comes along and just rips the oxygen right off of the copper. Since the carbon gained oxygen, we say it's been oxidized. And because the copper lost its oxygen, we say it's been reduced. Pretty straightforward, right? But what happens in reactions where there's no oxygen at all?
That's where the modern and frankly much more powerful definition comes into play. If you drop a zinc plate into acid, there's no oxygen getting passed around. Instead, something way more fundamental is happening. The zinc atoms are literally giving their electrons away to the hydrogen ions in the acid. Zinc loses electrons, so it's oxidized. Hydrogen gains them, so it's reduced, and it bubbles away as hydrogen gas. See, that's redox in action, without a single oxygen atom in sight.
And that right there is the key. By defining redox by the transfer of electrons, not just oxygen, we can suddenly understand and explain a massive, massive universe of chemical reactions. Everything from how batteries work to how our own bodies get energy. It's just a more fundamental, more useful way to look at it.
So this is not just some abstract thing you learn in a chemistry class. This simple partnership of giving and taking electrons has, quite literally, shaped the entire history of our planet.
We can actually look at history through this chemical lens, and it's pretty amazing. Here are 3 revolutionary moments, all powered by redox. Let's dig into each one. First up, photosynthesis. Billions of years ago, these tiny organisms called cyanobacteria figured out how to use sunlight to perform a neat redox trick, splitting water molecules. In doing so, they released a waste product, which just happened to be oxygen. Over millions of years, this waste completely filled our atmosphere, making it possible for complex, oxygen-breathing life to evolve and even creating the ozone layer. I mean, think about that. A single redox reaction changed an entire planet.
Okay. Fast forward a couple billion years, and now it's our turn. Humans learned how to control redox. To get useful iron, you have to get rid of the oxygen that's stuck to it inside the rock. We call this smelting. You're basically using carbon monoxide to steal the oxygen away from the iron ore. The ore gets reduced, leaving you with pure iron. This discovery kick-started the Iron Age and completely transformed human civilization with stronger tools and weapons.
And then came the Industrial Revolution. So what is burning, really? It's just oxidation happening really, really fast. By rapidly oxidizing fossil fuels like coal, we unleashed massive amounts of energy. That energy powered steam engines, factories, trains, you name it. Our mastery of superfast oxidation launched the modern industrial world. So we've seen how redox built our world on a massive scale. But what's really cool is that it's also happening all around us, every single day, in ways you might never expect.
Seriously, it is everywhere. You cut an apple and it turns brown on the counter? That's oxidation. You shake one of those disposable hand warmers to heat up your pocket? That's just the rapid rusting or oxidation of iron powder. From bleaching your clothes to creating the beautiful glaze on ancient pottery, it's all powered by this one fundamental chemical partnership.
But talking about it is one thing. To really see this electron transfer happen right before your eyes, let's look at a classic and frankly beautiful experiment.
All right, here's the setup. We start with a shiny copper wire and a totally clear solution of something called silver nitrate. Now watch what happens when you put the wire into the solution. It is just incredible. The solution slowly starts turning this amazing shade of blue. And the wire starts to grow these delicate, feathery crystals of pure silver. So what is happening here? Well, it's our redox partnership at work. It turns out copper atoms are just more willing to give away their electrons than silver ions are. So the copper literally hands its electrons over to the silver. The copper gets oxidized and dissolves into the solution. That's what makes it turn blue. At the same time, the silver ions take those electrons, get reduced back into solid silver metal, and form those incredible crystals. It's the perfect visual of that electron swap.
Seeing a reaction like that makes you realize just how powerful this process really is. And the next logical step, of course, is figuring out how to control it for our own benefit.
Let's circle back to our very first example, rust. We know that rusting is just the slow, unwanted oxidation of iron. So now that we understand the chemistry behind it, can we stop it from happening?
Absolutely. And the goal is actually really simple. You just have to stop oxygen and moisture in the air from touching the iron. The easiest way to do that is to put up a physical barrier. A coat of paint, a layer of oil or grease. These simple methods physically block the oxygen, stopping that redox reaction of rusting right in its tracks.
Okay, so preventing a reaction is one thing. But what happens when we take this ancient chemical partnership and use it to build the future? This is where it gets really exciting. Take a hydrogen fuel cell. It's a marvel of controlled redox. Inside it, hydrogen is oxidized, it gives up its electrons, and oxygen is reduced by taking them. But here's the genius part. Instead of just creating heat, we capture the flow of those electrons as electricity. And what's the only byproduct? Pure water. That's it. It's an incredibly clean, efficient way to generate power, and it's already being used in things like cars and even spacecraft. So when you step back and look at it all, from the photosynthesis that gave our planet's first breath of oxygen, to the smelting that built our cities, all the way to the clean energy that could power our future, this simple give and take of electrons is one of the most fundamental forces shaping our world. It's a partnership that's been at work for billions of years, and understanding it gives us the power to build the world of tomorrow. The only real question left is, what will we do with it next?